Hi everyone, welcome back to the chemistry lecture series. We're going to be talking about today specifically regarding dimensional analysis. We'll also maybe talk a little bit about sig figs, or although I might put that in another video, depending on how long this one is. So let's get into it here. What is dimensional analysis? It sounds really like mathy, like maybe something you'd hear in calculus, but it's really simple. And all dimensional analysis does is converts units to other units. And we're going to use this technique quite a bit, so it's good that you get the fundamentals here. I'm going to start with a very brief introduction of what it is, the conventions we use, but then we're going to jump right into practice problems because it's one of those things that you just have to practice. It can be complex at first, but once you get the hang of it, I think it will be okay. We're also going to be using prefixes here today as our main source of whatever here. And we're also going to talk about density and stuff like that. So keep that in mind. And I want you to be critically thinking here that this is a really fundamental part of chemistry. This is, at least on the math side, the most important thing that a day-to-day chemist will do. We do a lot of dimensional analysis. An organic chemist will do a lot of it. An analytical chemist will do a lot of it. A forensic chemist will do a lot of it. So just keep that in mind. So like I said, dimensional analysis is just converting units from one form to another. A good example of this would be, let's convert 50 centimeters to meters. Well, how could you do that? Okay, well, you could say, I just know that 50 centimeters is half a meter. But let's say you didn't know that. How could you mathematically prove that that's the case? In fact, what if maybe you had, I don't know, something like 52 centimeters. Now maybe less of you would know exactly how many meters I have. So there's a mathematical treatment that we can do to really solidify the answer no matter what situation we're in. No matter how weird things get, we just don't have to think about it. We just set something up and do the math. That's what we're going to do. And it requires using these kind of trees. And the way that I like to show this is you have a little line, you have an X, you have a line, you have an X, you have a line, and you output some number. That's typically how these are set up and how you'll see it in probably a class. Alternatively, you might see it something like this, but they're synonymous, and we'll see why. I'm going to go with this one up here. And in essence, what you're doing is fractional math, but you're presenting it in a way that doesn't look as fractionally as math, and it's a stepwise kind of thing. Each successive little bump is going to be a step. So in the case of converting centimeters to meters, we'll have just one step. And again, this is something that you're just going to have to learn and get a grasp on. Okay, so let's convert 52 centimeters to meters. So step one is to write what you're given. In the first blank. So no matter what you're given, you're always going to put your whatever you're given right here. So 52 centimeters. I want to make a distinction. If you had a density, let's say that density equals 3.2 grams per liter, so 3.2 grams of substance in 1 liter, you would write that given as this, 3.2 grams over 1 liter. Okay, so keep that in mind when you're working here. That what you're given can go top and bottom, and it's dependent upon the fraction that you get here. So in the case of the density, it's 3.2 grams on top over 1 liter on bottom, because we know that's what density is telling us. Okay, so let's do the conversion here. What we need to do is define what's called a conversion factor, and that's the fraction that's going to go here. Now, the way that you want to set this up, if we remember what fractions do, if I have a fraction, or if I have a number a, and then I multiply it by b over a, what do I get out as a result, or how can I simplify that? A times b over a. Well, you would say that the a's would cancel and you'd be left with b. This is the fundamental idea of dimensional analysis, is that we're going to cancel the units that we don't want and get the unit that we do want, in this case, which is b. So in the case of this, what we're going to do with our units is put the centimeters on bottom, but the meters on top, because what we're going to do is after we do this calculation and we define this what we call a conversion factor, the centimeters will cancel out and we'll be left with meters. Hopefully that idea makes sense. If not, I hope just an example will kind of show you, and we'll do a ton here today. So what you can do with your conversion factor is you can think about it or you can memorize it. Now, the way that I approach this is I just think, you have to critically think about this. If you have 1 meter, how many centimeters make up that whole meter? Well, we know if we look at your chart that we talked about in the last lecture, we know that for every 1 meter base unit, you have 100 centimeters of that prefix unit. So we know that for every 1 meter, there's 100 centimeters. This is a conversion factor. It's just relating the two in a fractional form. It says for every 1 meter, there's 100 centimeters. And look what happens. If we treat this as a fraction, right, a number times a fraction, the centimeters will cancel on the bottom and your output will be in meters when you calculate it. Okay, so let's go ahead and calculate it. What we're going to do is, and sorry, I should be writing my steps. Step 2 is to write that conversion factor. And right now, the only conversion factors that you will see are going to be ones that relate prefixes. When we get into like moles, molarity, you're going to see a lot more conversion factor reactions. You're going to see these things get kind of exploded, and you get all these sorts of really cool conversion factors. But it's not hard, so stay with me here. Okay, so let's go ahead and do it. 52, and how you calculate this is multiply the top, divide by the bottom, and then for number 4, if applicable, not convert, do the calculation for the next conversion factor. If possible. So let's think about that. If possible, do the next conversion factor. If we, for example, had another conversion factor here, you would first, so for the first one, you would say 52 times 1 divided by 100. Then you go to the next one, times blah, 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 divided by the numerator. And you keep going until you're out. That's dimensional analysis. And all we did here was convert the centimeters into meters. So 52 divided by 100, well, it turns out that's 0.52 meters, okay? That, in essence, is dimensional analysis. Now what I want to do is show you when you might see step 4. And step 4 occurs when you have conversions where just thinking about the units are really, really hard. And I'll give you a good example of that. Let's say, for example, instead of 52 centimeters to meters, we talk about 52 centimeters to kilometers, okay? So let's do step 1. Let's make our tree. Let's do just one out. 52 centimeters. Well, what's the conversion factor to kilometers? Do you know that off the top of your head? A rational chemist might be able to figure it out, but it's not the most intuitive thing, and it's not worth your time to be thinking about these things. Instead, what we're going to do is define 2 conversion factors, and let's see what this looks like. Let's first convert to the base unit. You should always remember what the base unit conversions are. So, for example, 1 meter is 1,000,000 micrometers, micrometers, or 1 meter is 1,000 millimeters, or 1 meter is 10 decimeters, that kind of thing, or 1 meter is 0.001 kilometers. These are things that are very fundamental for you to understand and just get a rational grasp on. Okay, so let's define how we go from meters to centimeters. So we're going to write our conversion factor such that the unit that we don't want cancels out and we're left with the unit that we do want. So we just did this, right? 1 meter is 100 centimeters. And look what happens to the units. This is very important. Centimeters cancel, you're left with your meters up top. But let's take this one step further. We're going to skip step 3 for now, and we're going to write another conversion factor. Okay? Well, we know that 1 meter is how many kilometers? Well, you might know that as 0.001. However, here's a more intuitive way to do it. Please just think about this rationally. Instead of defining 1 meter, well, what's 1 kilometer equal to compared to a meter? Okay, what is that? Well, that's 1,000 meters, right? We know that 1 kilometer is just made up of 1,000 meters. And notice how much more simple the math is. We don't have to divide by a decimal. It's a lot simpler. So look at how the meters cancel now, and we're left with kilometers. So now we're going to go on to step 3 and step 4, where we're going to multiply the top, divide by the bottom, then go to the next one, multiply by the top, divide by the bottom, and let's see what we get. So we're going to take the 52, we're going to multiply it by 1, we're going to divide by 100. Then what we're going to do is we're going to go to the next one. We're going to take whatever output we get here and now multiply it by 1, divide by 1,000. And what you're going to get as your output, the amount that you get in kilometers, is 5.2 times 10 to the negative 4 kilometers. So then we can say, well, it's fair to say that 52 centimeters is 5.2 times 10 to the negative 4 kilometers. Or in another way, if we aren't so familiar yet with scientific notation, this would be 0.00052 kilometers. So it's a fraction of a kilometer, a very, very small amount, those 52 centimeters. Okay, let's just do some more practice here to make sure we got it. We'll do 3 examples and then we'll call it. This is just an introduction to dimensional analysis, or we'll also talk about sig figs, I suppose, as well. But there's not a whole lot here, but another big point is word problems, because these kill chemistry students for some reason. And to me, it's always been like, oh, well, you get context, it's a good thing. But sometimes they can be a little confusing, because what are they talking about, right? That might be a little confusing to you. Okay, so let's say that a certain substance has a density of substance A is 5.2 grams per liter, and we have 2 liters of it. Then I want to ask, how many grams of it do we have? So if you need, copy these to your notes, because I'm going to go ahead and erase it here. But what this is saying, in essence, and I'm going to visualize it for you, hopefully, is that contained within, let's say that this is some finite 1 liter. In this 1 liter volume, there is all this stuff in here, and there's 5.2 grams of that in that 1 liter. So how much is in 2 liters? Well, intuitively, you'll just multiply that by 2, right? And you'd say 10.4. But let's prove that, right? Because if we had another liter, like something like this, with the same amount, right? It's just double that, right? So the total amount of mass in there, just double this number. But let's prove it with dimensional analysis, because sometimes it's not so cut and dry. What if you had 2.334 liters? What is it then? Let's go ahead and define the math. So using step 1, we're going to write what we're given. But remember how I said earlier, what you have to do is take the 2.5 grams and put it over 1 liter. Okay? Now what you have to do is your conversion factor isn't going to be a ratio between things. It's going to be just 2 liters, right? Because what you want to do in dimensional analysis, this is extremely important, is that you cancel out the liters. The units that you don't want need to go away, and it's the best way to check your math. If the units cancel and you're left with what you want, you're going to just get what you want. Granted, everything is accurate there, but let's do it. So we're going to take this number, 5.2, it's over 1. and then multiply it by 2, right? We could divide by the bottom, but we could just treat this as if there was a 1 there, right? Because any whole number or any number over 1 in a fraction is just the number in the numerator. And in fact, when we do this, we're going to see that it's 10.4 grams. So that's how we use density to do these kind of things. Let's spice it up a little bit. Let's ramp the difficulty. This is the hardest that you will see at this point before you start dealing with moles. Okay, so imagine that you have a density now of 5.2 grams. Let's now say that we have only 1.75 liters. Actually, let me change that. Maybe 1.27 liters. 1.72 liters. How many micrograms do you have? Okay. So notice there's a lot going on here. I really ramped up the difficulty. We're going to have to do that dimensional analysis with density that we saw, but we're going to get out grams, and what we have to do then is convert it. So this is going to be a very long dimensional analysis problem. So let's write what we're given. It's 5.2 grams over 1 liter. But recall that what we did last time, in literally like 2 minutes ago, was multiply by the 1.72 liters on top, which is going to cancel liters and give us grams. But when we output grams, that's not exactly what we want, right? We want it in a mass, which we have. It's just not in micrograms. So let's think about this. And this is how we're going to do this. We're going to do a conversion factor like we've seen. So on the bottom, we want grams such that it cancels out the grams. But on top, we want the microgram. Okay, so what relates the two? What's the relationship between a gram and micrograms? How many do you have? Well, I know that for every 1 gram, I have 1,000,000 micrograms. You could also write this as 10 to the 6 if you want to just shorthand it. But this is the entire dimensional analysis. Now look, grams, even though they're separated by a little conversion, right, they're still canceling, right, because they're top and bottom, but you still have micrograms on top. So when we compute this, we have 5.2 times 1.72. So we're going to multiply the top, and then there's nothing to divide in the bottom, so we're just going to multiply by this number again. 1,000,000 is what we're going to multiply by. And then we're just going to divide by 1. Right? Because 1's in the denominator. And what you get out is 8.94 times 10 to the 6 micrograms. Okay? Which would be this number. So roughly 9 million micrograms, roughly. So that is dimensional analysis in a nutshell. It can be challenging at times. And what we're going to notice is the hardest part for a lot of people is understanding the map, right? How do you do it? And to be honest, there's no real right way to do it. Okay, I could have done the microgram conversion first and then the liter conversion that we did. So I could have switched these two and that would have been okay. So it's flexible. Even though it feels restrictive, it's really flexible, and you can do really cool things with this. Anywho, guys, that's going to wrap up dimensional analysis. Now I want to talk about significant figures. And we're going to start with a little thought experiment. So Bobby's in the lab, right? As Bobby is. Right, here's Bobby. Kind of looks like me a little bit, I suppose. I don't know why I tried to give him hands for feet. That was weird. But let's say that Bobby has a beaker, and he has some substance that he isolated. So maybe in your labs you've done this, right? You've worked with this thing called a balance, right? that that you put a little thing on. So you're going to put this beaker onto the scale and it's going to output a number. Okay, let's say that the number that you get out is 274.1339 grams. Okay? Or actually, let's say that it reads 230 grams. Okay? But let's say that Bobby did some math. Okay, with this number, let's say, I don't know, he did a little conversion or two, and let's find that of the 230 grams of that beaker, that the important compound in there was, I don't know, 15.99321 grams. So he got a really precise number, right? But is it accurate to extrapolate that number out of there? Well, look at the accuracy of this number. It's very vague. 230 grams is not, real precise. But this number is incredibly precise. Is it accurate to say that? Well, the answer to that question is no. So in this number, you have what's called two significant figures, right, in this number. But here you have 1, 2, 3, 4, 5, 6, 7. 7 significant figures, which is absolutely crazy. You cannot go from 2 to 7 sig figs. All right, we're going to learn the rules. We're going to learn how to count them, and then that'll be it. All right, so hopefully that kind of opens your mind to the idea of accuracy, precision. How do I report things on a lab report? Let's talk about sig figs. So counting sig figs goes something like this. If we have some number like this, we call these leading zeros. And we call these trailing zeros. All right, and rule number 1 is that all non-zero numbers count when we want to figure out the number of significant figures, okay? The numbers that actually matter, okay? In counting that, we need to consider the following rules. All non-zero numbers are significant. Okay, not only that, leading zeros are always insignificant. But number 3 is that trailing zeros can be significant. All right, so trailing zeros can be significant. And I'm gonna use this term quite a bit. When you see if with another F, it means if and only if. So trailing zeros can be significant if and only if there's a decimal point. And in the case of this number, there are trailing zeros and there is a decimal point, so these are significant. Where you might see where this fails, for example, is if you had, for example, 230, right? This zero here, even though it's trailing, is not significant. So let's do some examples of this. I'll let you guys write the rules down quick, but then I'm going to go ahead and erase everything. Okay, so let's consider the following numbers, and I want you to tell me, for each digit, is it significant or not, and how many overall significant figures are there? Okay, this number, let's consider how many significant figures, number by number. Remember, rule 1, all non-zero numbers are significant, so all 3 of these are significant. I'll denote that S. Are trailing zeros significant? Well, if there's a decimal point, there is. Is there a decimal point here that we see, that I explicitly showed? The answer to that would be no. So I'm going to write N for these for no. Okay, so the overall number of significant figures is 3 sig figs. All right? Why do we have this convention here where trailing zeros maybe can or cannot be significant? Well, if I then change the number to this, and I specify to you that there's a 0.0 here, the significant number amount raises. Everything here is significant, which is kind of crazy to think about. But 1, 2, 3, 4, 5, 6, 7, there are 7 significant figures. That small change just by putting a 0.0 changes everything. And why is this? Well, here it's vague. You're just giving a rough estimate. Maybe this is like a distance of 133,000 meters. But if I specify to you that it's 133,000.0 meters, I'm telling you that there's accuracy there. I'm telling you whatever I used to measure that was so accurate that it was able to get to that level of significance, right, where it could get down to that 0.0 range of distance. Okay, so that's why that convention's there. It's critical that you get that. All right, let's just rapid fire some examples, and then we'll talk about adding and subtracting sig figs. So let's take the number 732.002, and how many sig figs do we have now? Notice I didn't specify a 0 in my rule. Those zeros are neither leading or trailing. What happens to them now? Okay, let's consider the amount of sig figs here. That's a sig fig. That's a sig fig. That's a sig fig. I know this is, right, because all non-zeros are significant. What about these guys right here? Are they significant? Well, if they're sandwiched, they are indeed significant. So if you want to add a fourth rule about that, go ahead. But the reason is because if I'm specifying this degree of accuracy, well, then this must be accurate too, or else how would I know that I have 0.002 accuracy? Hopefully that kind of makes sense. It's a little hard to justify it. So again, I know I said this a lot. It's just one of those things that requires you to kind of do it a lot to get it. Yes, they're all significant. Jeez. Lock in, Corbin, lock in. We have 1, 2, 3, 4, 5, 6. So overall, there's 6 sig figs. Okay, let's consider the number 0.0003275. Okay, what now? What is the sig fig count here? Well, notice leading zeros here. These are all not significant, right? But notice all of these are significant, right? Because what I'm doing is I'm specifying this degree of accuracy at the end. If I didn't have that degree of accuracy, I wouldn't have told you about it, right? So they're all significant. Thus, we have 5 sig figs. So if you need more practice on this, please do practice problems. Your textbook Chemistry 2E on OpenStax has amazing practice problems for you to look at. And, this could be part of it, where you can get... All right, now what I want to consider is when you add, subtract, multiply, divide, how do sig figs scale there, right? Because what you want to do when you add 2 significant numbers together and get out one combined significant number, what is the math behind that? What's the convention? And it turns out there's 2 ways. If you're adding or subtracting, you're going to go with the number, or you're going to round your significant figures to the least amount of decimal places contained within the things you're adding or subtracting. So I guess I should say this is adding or subtracting. All right, so if we take, for example, 23.5 plus 20.002, well, let's consider which one has the least amount of decimal places. It's going to be this one. So whatever this number comes out to, you're going to round it to the 10th place. I think that's what that is, the 10th place. Anywho, let's do this. What's 23.5 plus 20.002? Well, that's going to be 43.502, but notice I didn't round to a significant amount because the least amount of decimal places is this. Suddenly that 0.02 vanishes. It's gone. that is how we would report our number, 43.5. Okay, what about multiplying or dividing? Okay, you're going to use the least number of sig figs available. So maybe I'll just add a little 8 there. And I'll actually multiply the two together. That's important. So we have 72.9 times 2.178. How do we do this? Well, simply first just actually calculate what that is. So in my calculator, I'm going to plug that in. And when I get that, I get 158.7762. But how do I round this? Well, I'm going to go with the least number of sig figs, which this one has 3 sig figs, where this one has 4. So I'm going to round it to 3 sig figs, right? 5 and above, give it a shove. We're going to call that 159, okay? So hopefully what I was able to do in this presentation is tell you a little about dimensional analysis, tell you a little bit about sig figs, and that's all we're going to talk about here. Very critical. These are kind of minor, but remember, when you're asked on your exam to evaluate sig figs, you're going to be tasked with remembering these rules. Multiplying, dividing is least amount of sig figs. Adding and subtracting is least decimal. And I'll be honest before I go, when you do this, it really feels intuitive, like you don't even think about it at some point. You're just like, yeah, it's that amount of sig figs, or no, it's that amount of sig figs. It just comes naturally over time, like most things in chemistry. That's the beauty of it. It all just comes with time. So, anyways, I hope you enjoyed this. If you did, drop a like, comment, subscribe. Have a wonderful day. Bye-bye.